Welcome back to OCR MEI Further Mathematics B. Today we're doing chapter 3.4, Plane Geometries. So planes in the 3D space have a lot of different orientations, but they do not actually need to intersect. In any cases, they can just be in an arrangement such that it's like a parallel line. They can lie completely parallel to each other, and there won't be anything that you can solve for. There are 5 general scenarios, and I'm going to outline them here. And next video, I'm going to actually talk about the different types and how to get them. For now, just recognize the fact that there are 5 different type of orientations. When we intersect a plane in 3D space, let's start with having a single plane. So if I have a single plane on a 3D space, then I in general can have a line if I look at it completely along the plane, or it can be an infinite kind of sheet if I look perpendicular or parallel to the normal. So in this case, this is looking perpendicular to the normal, this is looking parallel to the normal, and it can be kind of slanted downward diagonally with a surface area. If you look kind of at an angle to the normal. So these are ways to kind of visualize, like you can try to visualize the different scenarios, but the most important orientation is probably this one, the perpendicular to the normal kind of orientation, because this is how I'm going to demonstrate the 5 types of intersection that 3 planes can have in 3D space. Just as in 2D space you've came across simultaneous equations, you can have a line crosses another line and you will get a particular solution. This will be unique as a straight line. For planes, it's similar to straight lines. There are curved planes, which will be a curved surface instead. That would kind of be like how you can have a parabola with a line and then you have some arbitrary solutions. We're not going to talk about that during A-level. This is a bit too much. We will stick with straight lines in 3D, or in other words, planes, because planes are 2D. And on a 2D surface, a line is 1 dimension step down. For a 3D space, a plane is a 1 dimension step down, because 3D space step down is 2D, which is a surface. We can intersect these flat planes in 3D space. And I'm gonna start with just one plane, which is aligned perpendicular to our line of view. I'm gonna say that the plane aligns with its normal factor, if that helps the orientation kind of visualization. So now we're looking at this plane, and we can orientate another plane. This is a second plane, perpendicular, not parallel to the original plane, and so there won't be any solution because they won't cross. It's just as if you have a parallel line on a xy plane. They won't cross. Even if you do simultaneous equation on it, you wouldn't get anything. So that is one of the orientation for just two planes. There's also one that crosses. So if it's not parallel, it will definitely cross for a plane, for two planes. And it can be perpendicular, or it can be just kind of skewed here. And for two planes, these are the only options. But if I have another one, then we can split the scenarios. So let's hypothesize that we have two types. Type 1, we already have a parallel plane. Type 2, we do not have a parallel plane. We add another one, we can add it like this. Now it is 3 parallel lines on the plane, which is one of the 5 that we need to know. We can have one that doesn't is not parallel, which will give us the second one. These solutions normally wouldn't appear in the exam because they are kind of boring and they cannot be written as a good kind of question to ask. So the parallel cases are a bit less applicable, I guess. Then comes the important ones. So if I have a plane, two planes that have crossed, then I can cross another plane in a kind of slanted plane in this orientation, and that this point here will be a unique solution. So we have a dot as our solution. This is one of the most likely, I feel like actually this is the most likely scenario that will be a solution. But there are also other scenarios. So if instead of having that dot as a solution, we can have another plane that cuts like this. So now we have 3 solutions, and 3 of them are all different, which means that when you do simultaneous equations, you will get inconsistent results. Inconsistency is something that you need to look out for. Then after that, we also have another one which happens to cross at the exact same spot. And then we get some formation like a spider web. This is a consistent solution, which inconsistent and consistent will be the 2 main things that you need to look out for, because the examiner loves asking these 2 scenarios. Turns out they do not actually like this unique solution because it's relatively easy to deal with if you know what you're doing, that is. This can be done easily with matrix, so they wouldn't examine that often. For these 2, the geometry is called prism and sheave. So you need to know the word prism for this formation, sheave for this formation. As long as you know that this means consistent results, this means inconsistent result, then it should be relatively okay. The actual process of calculating these geometries. I will talk about that in the next video, but these are the 5 main things that I want you to know. So triple parallels, one pair of parallel and one that is not. That's 2 of the scenarios. Then 3 others are unique solution dot, a prism formation, and a sheaf formation. That's all for this video. There aren't any questions that I can give you at this point in time, so do take a break. And if you have any questions, leave it in the comment section, and I will see you on my next one.